J3, the double ball drop. This is a demonstration I did many years ago when I taught introductory physics. You have a small ball on top of a big ball, and you drop them, and then when the ball, lower one, hits the ground, it bounces to come up, but see, the other ball that's on top of it is still going down. So I'm going to sketch these two balls like this without any arrows and put the arrows to the side here. This is ball 1 after the bounce heading up, and then this is ball 2 heading down to collide. So 1 and 2. And up is positive. What's going to happen here is that the velocities afterwards will be V1 and V2, which we're going to solve. And I did this because you're going to see that this little ball takes off and goes crazy when you drop these like this. You have to be careful to line them up just right. But when I would get it right the first time, the class would be very impressed because it would smack and hit the ceiling. Let me show you why that's the case. Now, we can use our formulas from the earlier section. We don't need to rederive these. We can use formulas just like we use formulas in kinematics when we're doing homework. We just pull them out of our bag of tricks when we need to. So this formula here gives you the velocity of the first mass after the collision. And then there is the velocity of the second mass. And as I say, you look these up. Now the kinematic formulas, when we use those should be memorized. They're very, very basic and important. But these equations, nobody really remembers these equations. They look kind of weird, a little bit hard to remember. So we can just look these up. And here I'm copying them down from the earlier section, which we derived the long way, and we derived it using the shortcut. Now let's see, we're missing a 2 here. We need a little 2 there. Okay. So now we have everything. And the balls that I found, good balls that had good bounce, this lower one, M1, was 51 grams. And this top one here that was on top of it was 17 grams, which was kind of neat because 3 times 17 is 51. So that's a cool relationship. In other words, M1 happens to be 3 times M2. And here, U2 is minus U1, because if you drop any mass, the base is going to fall at the same rate. So U2 is about to do the collision. U1, the first mass is on its way up with U1, and it's going to then, boom, they're going to collide. So here we can prepare that. This is minus U1. This is minus U1. All right, balls drop from the same height. They reach the bottom with the same speed, and we're assuming perfect bounce, so that first one that bounces is going to have U1 coming up, the other one's going to be U1 going down, and they're going to smack together. So let's do it. What happens to the second ball is what I'm interested in, the light ball, the second ball. So the second ball is going to be here, 2 times 3 M2, because that first ball is 3 times that smaller one. And this is then going to be 3 M2 plus M2. That's what we're going to get there. So that first mass is 3 times the second one. The second one's the lighter one. And we're going for the speed of the lighter one. And then this is going to be here, plus this is going to be here, M2 minus 3M2, because that first mass is 3 times the light one. And then this is 3 times the light one plus the light one. All right, and this is then minus U1. All right, so what do we have here? We're gonna have 6 over 4. 6 over 4, the M2's cancel. That's gonna be 3/2. What do we have here? We have minus 2 over 4. That's minus 1/2. And here we have minus U1. So when we add these together, we're going to get 3/2 plus 1/2 U1. And that's going to be 4/2, which is 2U1. All right, so the speed that these balls reach the ground at, that second one on that collision is going to be going up with twice the speed. Now, here's a cool analysis. If I drop the balls from a height of h, then conservation of energy here, 1/2 mv squared is mgh. When the ball hits the ground, it's going to be going with velocity v. The height is related to the velocity squared. So if you double the height, then the velocity will increase by this formula. So what I'm interested in is given the v, find out what the height is. So the U1 is correlated with the height that I dropped it at, h1. But see, V1 is correlated, or here, let's use V2 because it's the light ball. V2 is correlated to the height that it's going to go after the bounce is h2. But what we're saying here is that the height is proportional to the velocity squared. So that means this one here is going to be U1 squared related. But see, this one has a 2U1. The V has double, so that means this is going to go up 4 times as high. That's what that's telling us. All right. So U1, the speed, if you drop here, height 1, when it gets to the bottom, it'll be going at speed U1, and if it's a perfect, situation, just go right back to the top. Now, no ball is perfect like that, but we're assuming the ball is perfect. Go back up. But if you're to achieve double this speed, then you have to be at 4 times the height. Because the rule is that the height that's correlated to the velocity when it reaches the bottom, or on a bounce going back up, is related to v squared. So since I have double the speed on its way up, when I square that, I will get 4u1 squared, which is 4 times the height. All right. Now, if you want to, work it out, you can work this out in exactly if the proportions make you a little nervous. Here, the m's cancel, and you get v squared is 2gh, and that means the height is equal to v squared over 2g. This is the general formula. So the height that's correlated with the u is u1 squared, c over 2g. And then the height, that 2 that's correlated with the, in this case, it would be 2 with these 2 u1s over 2g. That's going to be 4 times u1 squared over 2g, and that's going to be 4 times h1. So in other words, on the bounce, it's going to go up 4 times higher. So when I drop this at 1 meter, and it smacked against the ceiling. It went up to the ceiling. That is awesome. And then finally, I noticed that the big ball wouldn't leave the ground. So let's look at this. The big ball here, if you look at the big ball here, if you take the mass 1 is 3, of the second one, right, minus M2. And this is 3 of the second one, see, plus M2. And this is U1. And then over here, we have 2 times, and this is 3. This is the second one, so we just leave this one alone, M2. And then here we have 3 of the second one plus the second one, and that's minus U1. So what do we have here? We have 3 minus 1 is 2. 2 over 4 is 1/2. This is a 1/2. What do we have here? We have 2 over 3 plus 1 is 2 over 4. That's a 1/2. But guess what? Minus 1. Look at that. Minus U1. 0. What a coincidence. In fact, I noticed the ball would just stay on the ground. It's like the first ball just stayed on the ground, and the second one shot up like 4 times the height and smacked into the ceiling. Now, they have this toy or demonstration that helps you keep the ball straight, and also they have a multiplying effect. They have actually balls getting smaller and smaller and smaller, and the safety glasses. Dangerous. Do this. Want to be very, very careful. And here you drop this. The rod helps keep them aligned, because when I drop them freely, it's easy that there's an angle and it goes off to the side. So here you can drop it a little more easily and have the safety glasses. My grandson likes this, wears the glasses, and has a lot of fun, dropping that. The multiplying effect. They call that the seismic accelerator. And there's an Astro Blaster, is a similar toy.